Hi everyone, my name is Heini Väisänen. I work at the University of Southampton, and today I will talk to you about multivariate binary logistic regression. So the outline of today's lecture is here. So we will talk about what we mean by multiple logistic regression. We will talk about model selection. So how to decide which variables to include in your model, and how Wald-tests and likelihood ratio tests relate to model selection. So by multiple logistic regression, we mean binary logistic regression models where we have more than one explanatory variable. Like in other regression models, you can add more than one variable, and that indeed is usually the interesting part about conducting regressions rather than cross tables, for instance. The interpretation of the variables is similar to what you saw in the first video, where we had just one explanatory variable in our model, but we are conducting this interpretation while we are controlling for or holding constant the other coefficients. So normally we would try and add variables that are meaningful or might impact the outcome that we're interested in, but which are not always the main part of interest with respect to our research question. Like with binary logistic regression models where you only have one explanatory variable, interpretation can be made in three different scales: log-odd scale, odd scale, and predicted probability scale. And we will talk about the odd scale and the predicted probability scale today, but we will not talk about the log-odds because, as we discussed in the first lecture, it is not a very intuitive way to interpret these regression models. So I will approach this subject with an example. So I extracted some data from the Demographic and Health Survey of Ghana from 2008. And I was interested in studying which characteristics of women or mothers are associated with the likelihood of having received assistance from a healthcare professional in their most recent birth. And I have the following characteristics of following variables available in my dataset. So we know the quintile of wealth of the household where the woman lives, going from the poorest 20% up to the richest 20%. Then we know the number of children that she has. We know whether she lives in an urban or in a rural area. And then we know what level of education, what is the highest level of education that she has, whether that's no education at all, primary, secondary, or higher education. Here is some information about how these variables are distributed in our dataset. So when it comes to our outcome or our dependent variable, so whether the woman received assistance from a healthcare professional in their most recent birth, we have 58% of the women who received assistance from a healthcare professional. And the other side of the coin is that 42% did not receive help from a healthcare professional in their most recent birth. When it comes to the explanatory variables, the mean number of children in the sample was 3.5, and we have 2,144 women in our sample. So just keep in mind that this is not the mean number of children in the population of Ghana in 2008, because by definition, we only have women who have at least one child in our analytical sample, because we are interested in their experiences in their most recent birth. So you have to have at one child by definition to be included in our sample. Around 35.6% of the women lived in an urban area, and the other side of that coin is that around 65% of women lived in a rural area. When it comes to education, around 36% of women didn't have any education, around 24% had primary education, around 38% had secondary education, and around 2% had higher education. When it comes to wealth, in our analytical sample, the poorer health categories are are more populous than the richer categories, which might be linked to the fact that we are only looking at a selected group of people, so those who have at least one child. When we put all of these variables into a regression model, in a binary logistic regression model, here are the results. So we have first the urban-rural residents, then we have wealth, then we have education, and finally we have number of children as a continuous variable. All the other explanatory variables are categorical. When it comes to the columns that you see in this table, the first column that shows you results shows you the results in the log-odd scale. So the unintuitive scale, but the one that is quite similar to linear regression. Then the middle column shows you odds ratios, and the last column shows you P-values from Wald-tests. And I will come back to what that means. Usually, regardless of which software you use, whether you use Data or R or SPSS or some other statistical software, you will get lots of other things as well in your model, like confidence intervals and standard errors. And those are important as well. But today we will only talk about these three, the log odds ratios and P-values. So that's why I'm not showing the other values. So how do we interpret our model? What do these numbers actually mean? We could start by looking at the odds ratios and the interpretation in our scale. I'll give you a couple of examples that give you different types of variables. So I give you one categorical and one continuous variable, and also different directions of effects, so positive and negative effects. So let's look at wealth first. If we wanted to focus on the differences between the poorest category and the richest category, we could say that when controlling for education, number of children, and place of residence, those in the richest quintile have 13.7 times the odds of having had assistance at the most recent birth than those in the poorest quintile. And how do we know this? Well, if you look at the odds ratio column in this table, and you look at wealth, richest row, you can see that the value there is 13.75. So it's just directly taken from that column. And since the poorest is the reference category, it means that when we compare the richest and the poorest, the richest are almost 14 times as likely to have had assistance in their most recent birth. While we are here, we might observe that the odds ratio for number of children is 0.95. And if we look at the corresponding log-odd value, we can see that it's a negative number. So we know that when the number of children goes up, then the odds of having had assistance at birth goes down. And if we want to express in odds ratios or in odds scale, how much exactly do the odds reduce with each additional child, we could say that when we are controlling for the other variables in our model, each additional child reduced the odds of having had assistance at the most recent birth by 5%. And the 5% comes from the calculation that I showed you last time, that you can use when you're doing interpretation in odds scale. So you take the odds ratio, 0.95, you subtract 1 from that, so 0.95 minus 1, and then to turn that into a percentage, you multiply that by 100, and we get -5. So that means that for each additional child, the odds reduce by 5%. More generally, when it comes to interpretation in as odds ratios, what we do when we interpret these model results in the odds scale, we calculate the ratio of the odds of the categories of interest. So the ratio of the odds of the poorest category and the richest category, for instance, for the wealth example that we just saw. And that's why they are called odds ratios or ORs. So for categorical variables, we calculate the odds ratio so that we compare the other categories to one reference category. And this is something that you already know from logistic regression. It's just that from linear regression. It's just that the difference multiplies rather than is additional, like in linear regression. For continuous variables, the odds ratio expresses how much the odds of the outcome being equal to 1. So in our case, the woman having had assistance at birth increases when the continuous variable increases by 1 unit. And as soon as you have the log odds scale results, you can calculate the odds ratios by exponentiating the estimates on log odds scale. Like we discussed last time, you can also interpret these results on probability scale if you calculate something that we called fitted or predicted probabilities. And the formula for doing that is here. So we figure out what the probability, or pi, is by exponentiating the equation of interest, dividing that by 1 plus the exponentiated value of the same equation as above. So when it comes to the equation of interest, we have to decide what we want to calculate. So as you might remember, the probabilities, these fitted probabilities, depend and are very different depending on which values of the explanatory variables we choose. So we might be, if we have a lot of continuous variables in our model, we might want to put everything in there as their means and kind of calculate the average predicted probability. If we have categorical variables, maybe we want to choose the most frequent category to kind of find this average experience. Or there might be other values of interest that would be relating to our research questions. Or we could, if we're using software to calculate these probabilities, we can leave them as observed. But that's not something that I will talk about today. But if you do the exercises related to this lecture, then you will see how that works. So I will just give you an example of how you would calculate these probabilities by hand. So let's say that we're interested in knowing what is the probability of having had assistance at most recent birth if the woman is living in an urban area, belongs to the poorest wealth category, has no education, and has 2 children. And when we plug in the values in this equation, we need to remember to use the log odds scale. So just to remind you, here's the table again, and I've highlighted the values that we need. So for place of residence, the woman lives in an urban area, so the log odds value that we need is 0.95. For wealth, poorest category is actually the reference category, so it means that its corresponding log odds value is 0, so that cancels out from our equation. Then for education, we have minus 1.55, and for number of children, we have minus 0.06. So when we plug these in to the equation, first we start with the constant, which in our case is 0.53. Then we plug in the value for living in an urban area, 0.95. And then because that is a categorical variable, we multiply that by 1. Then we plug in the value for having no education, minus 1.555. And again, that is a categorical dummy variable, so everything zeros and ones. So this is 1, we multiply by 1. And then finally, we want to know the probability for someone who has 2 children. So the minus 0.056 for having children, we multiply by 2 because there are 2 children. Then we exponentiate this, divided by 1 plus the same equation. And if we solve this equation, we get 0.458. So that means that the probability of someone who lives in an urban area, is in the poorest wealth category, has no education, and has 2 children, the probability that they had assistance from a health professional in their most recent birth is around 46%. So just to sum up, log odds, we can do interpretation in log odds scale, but it's not very intuitive. Odds ratios tell us about the relative differences and apply to the entire scale of a continuous variable. Probabilities tell us about the absolute levels of risk, and when we calculate them, we need to decide at which values the other variables are held. It does not apply to the entire scale of a continuous variable, but it is often the most intuitive option, so you might want to calculate the range of probabilities rather than just one like I did here. And usually you wouldn't do this by hand, but using software. Then a few words about model selection. So I haven't talked about p-values at all yet. So let's take a look at what these mean in a logistic regression context. So the thing that you normally see printed when you conduct these models using software is something called Wald-test. So it's very similar to t-test in OLS regression. So you kind of already know how to deal with it. And especially for continuous variables and binary categorical variables, it is a very useful way to assess significance. For dummy variables, unless you're conducting a joint Wald-test, it is slightly less useful because it only tells you the significance of an individual category from the reference category. So what do I mean by that? Here we have the p-values from our model. And if we look at the first variable, place of residence, we can see that that is associated with a very small p-value. And that means basically that place of residence is important in this model, and there is a difference between urban and rural populations in the population, or it's very likely that this difference also exists in the population. When it comes to number of children, so the last variable that we added to the model, which is the continuous variable, we have a p-value of 0.021, which at the 5% level again tells us that number of children is significant in this model, which means that we expect this association to also exist in the total population. However, if we wanted to look at wealth or education, we wouldn't be able to say just by looking at these p-values whether the dummy variable as a whole is significant, especially for education where we have a mix of large p-values and smaller p-values. So no education p-value 0.041, but then for secondary education 0.276. So the only thing that we know so far is that no education is significantly different from higher education, but secondary education isn't significantly different from higher education, but we're not sure if education as a whole is important in our model. But we could use the likelihood ratio test to figure out whether education or wealth matters. And how this works is that whenever we conduct a binary logistic regression model, we find the estimates by maximizing the log likelihood, or LL. And the higher the log likelihood is, the better the model fits the data, so the better the model is. If we take this value, multiply it by -2, we get something that we can use to test differences between two models. So if we calculate the -2LL value for two nested models, then by nested models I mean that there are some variables that are in common, and then one of the models has more variables than the other. This difference follows a chi-squared distribution, which you might already know from having conducted chi-square tests in cross tables. As you might remember, this distribution is different depending on how many degrees of freedom you have. And in a logistic regression context, we calculate the degrees of freedom by looking at how many parameters we have in each model and the difference in the number of parameters. The more complicated model always has a smaller -2LL value, which means that the fit is better, but this reduction in this value is not always statistically significant. And the likelihood ratio test tells us whether it is significant and whether we should keep that more complex model or go with a simpler one. So how does this work? Let's take a simple example with model 1 with the same Ghana example. In model 1, we just have number of children as an explanatory variable. And in model 2, we have number of children and wealth as explanatory variables. And in a likelihood ratio test, we are testing the following hypothesis. The null hypothesis is that there is no difference between the models, and the alternative hypothesis is that there is a difference between the models. Here are the results if we calculate by hand. So the likelihood value for model 1, so the one that only has number of children, is -1410, or 1014 and 10. If we multiply that by 2 and change the sign, we get 2,820. For model 2, the minus 2 LL value is 2,285.88. If we calculate the difference between these two, we get 534.36. We have 4 degrees of freedom because our wealth variable was a dummy variable with 5 categories, 4 of them which actually appear in the model because one of them is the reference category poorest and it doesn't do anything in the model other than being the reference category. And if we compare that to the chi-square distribution with 4 degrees of freedom, we get a very small p-value. So we conclude that adding wealth to a model was statistically significant and we should keep it in the model. So just to sum up, likelihood ratio test is often the most important tool that you will compare models, especially if we have interactions or big categorical variables. And normally you would do this using software, as you will see from the practicals associated with this lecture. You can also use the Wald-test that is automatically printed for you by most software to get information about statistical significance. And other than statistical significance, remember to use theory and previous research in guiding you when you're selecting which variables to include in the first place and in which order.